Now that we have our wave equation in this form where P and Q have these complicated expressions, you're beginning to get a sense of the tropical dynamics in terms of the wave mean flow interactions. This is the form. You have d squared v dy squared plus py dv dy plus qyv, where you know py has the background flow in it. So if you set the background flow to 0, you're going to get this to be 0, but this is still going to be alive. That gives us this equation. If you set u bar equals 0, no background flow, which means the slope, the meridional slope of the sea surface height is removed, then py equals 0. Qy is omega squared over c squared minus beta k over omega minus k squared minus beta squared over c squared and y squared. Despite these complicated looking equations, we are still dealing with a fairly simplified system in terms of simple background stationary state and simple wave number frequency without the 3D structure to it, which we will add soon. But this is now expressed in terms of the Doppler shifted frequency being the intrinsic frequency because there is no background flow. Right? So then the wave equation becomes real oscillator. d squared v dy squared is this coefficient of the waves and planetary vorticity times v equal to 0. I think all of you now know that this is a canonical wave equation. So py is 0, qy is this expression, and then vy can be written as the capital Vy, which is the mode function, times exponential minus 1/2 integral of py dy when you have obviously py is not 0. So for the full case you end up this equation, and you can write that as d squared v dy squared plus this is capital gamma squared as a function of y times v, where gamma is the refractive coefficient. I think you can call it the refractive index or yes, we can call it the refractive index. I think everybody knows what a refractive index is. That's how the waves change. For example, if you're thinking about light, if you put a stick into the water, it's going to look bent because the light has gone through a different density compared to air. And in the tropical system you have properties of the system varying, and waves travel through them. You're going to have refractions. Okay, so this is the harmonic oscillator that is essentially what we were after. So the refractive index squared of a wave is given by this qy minus 1/2 dp dy minus 1/4 py squared, where py is the complicated function we saw in terms of the mean background flow. So u bar here is u bar y, which is where we got py. If u bar y is py is if u bar is 0, py is 0, then gamma squared y just becomes qy. So we have to still remember we are on the equatorial beta plane. So we basically translated these governing equations with linearization into this wave equation. And before we go to the upper ocean, I should point out that there are turning latitudes. So this solution is obviously going to be of the waveform at low latitudes and exponential beyond a certain latitude. Those are called turning latitudes. So between the turning latitudes, we will see examples later on. It's like having a potential well, which means there is energy trapped which cannot be converted to other forms like potential to kinetic and so on. So you have a well in which waves can bounce around, be modulated by the background state, and so on and so forth. And the turning latitudes will turn out to be important in terms of the tropical dynamics in the ocean and the atmosphere, which are obviously a function of background flow as well as the other details that we haven't considered, like the vertical structures. So we'll do an example of the vertical structure of the atmosphere later on in this chapter and look at the coupling then between the horizontal modes and the vertical modes. Okay, so complicated, but still the simplified versions of the complicated problem. Okay.